Okay, let's start. So in the last class, we saw the motivation for using differential signals, right? And we also saw the difference between a pseudo differential and a fully differential implementation. So what's the difference? The pseudo differential. The common mode is poor in pseudo differential. So the simplest fully differential circuit or the fully differential op amp was our diff amp with a resistive load. And we also saw this common mode half circuit, differential mode half circuit, and so on, right? And in general, fully differential circuit might look like this. So we'll have two identical copies of the network. So here is where we apply the input, and say the outputs are taken here, and you will have some network in common like this, say NC or something. Okay. So now if I apply a differential input like this, what will be the differential mode half circuit? I'll have N here, so right side is grounded, so I'll apply the input here and take the output here. Now similarly, if I apply a common mode input, say VC or VIC, what will be the common mode half circuit? Yeah, so again the idea is these two potentials are same, so I can short them, and it's as though I have put two identical networks in parallel. So now it will look like this. So we'll have twice the network essentially. The output is here, and what happens to NC? Same. That will remain same as such. Okay. And usually this is what will provide you the common mode rejection, right? Because this is the thing that is getting added extra when you compare to the differential mode half circuit. Okay, cool. So if this is fine, let's I want to highlight 2 points. Firstly, say you have an op amp with a single-ended output like this. You know you can have an inverting amplifier made using the op amp, right? This is VA and V. Now we have a fully differential op amp. So let me draw that. So it takes two inputs and gives you two outputs like this. So now my input is differential and the output is also differential. So how can I form the inverting amplifier here? Yeah, okay, right now the way I've written is this is plus and minus, so no issues, right? I mean, this is plus and minus, so I can form the feedback like this. Okay, so we'll have basically two resistive feedback networks like this. Make sense? So this is my input and this is going to be my output. Okay. Again, the way to arrive at this is again straightforward. You say you start with the single-ended structure, you try to have an identical copy. I'll just flip it around like this. Right, so now this is going to be my input and this is going to be my output, and then you can reduce it. This is basically not relevant, so you can convert it like this. Okay. Great. Now we also know if we have an op amp with a single-ended output, just like how we have an inverting amplifier, what is the other amplifier we can form? We can have a non-inverting amplifier. So let's say it is like this, the input is here, same thing, right? This is grounded. So now I have a fully differential op amp. So now how do you suggest we can form an inverting amplifier, non-inverting amplifier with this? So in the single-ended case, how was the non-inverting amplifier formed? We have applied input to one of the terminals and the feedback is formed around the second. So can we do something like this here? I mean, if we assume that if I assume that the input is applied here, this will be used for feedback or vice versa, right? So bottom line, we can't form a non-inverting amplifier with this. Okay. So you can't. I mean, this you can do, but this you cannot form. I mean, unless you configure the op amp such that it has 4 inputs and 2 outputs, which will not see the conventional stuff will not have it. So unless we have a scenario like this, you cannot form a non-inverting amplifier like you have with a single-ended output op amp. Okay. But again, this is not a great problem because see one of I'll come to that. So one of the reasons to have non-inverting is, what is the difference between inverting and non-inverting amplifier? Yeah, I mean, this gives an inverting gain, this gives a non-inverting gain, isn't it? So here, the way I have drawn the inverting amplifier, the gain I'll have is minus R2 by R1, right? If this is R1 and R2. Now let us say I want to get a gain of plus something in this circuit. What is the simplest thing I can do here? Yeah, I can basically reverse things, right? Because now my output is not defined with respect to a ground. These are 2 wires, isn't it? So what I can easily do is crisscross the output like this, right? So now I will define the output like this. That is going to be inverting. So from here to here you have a free gain of minus 1, right? But if you have a single-ended output op amp, you will have to have, if you want to invert the gain, you need to have another op amp configured with the gain of minus 1 and do it. Okay. Besides this change in the gain, change in the sign of gain, what is the other difference between this inverting and non-inverting amplifier? Gain is different, but let us say we can change the resistors values accordingly, so that's not a problem. What is the other difference you can see here? Sorry? What about the input? Sorry, can you say more? Yeah. So yeah, that is correct. He is saying here the input is applied to the non-inverting terminal. Here it's applied here. So what change does it imply? I mean, what is the difference then? Input resistance, right? So what is the input resistance looking here? What is it? I mean, okay, see, what is if the op amp is ideal, what is this potential? 0. So what is looking in resistance? R1. What is the input resistance here? Infinite. So, in fact, this is basically sensing your voltage with an infinite input resistance. So it doesn't draw any current from the previous circuit and senses it. So in a way, this could be good. But one crucial difference between these two is the fact that, see again, if this op amp is ideal, the virtual ground here is 0. That everyone is fine. Let's say now we have a finite gain of some A. Okay. And if my output is V0, what will be this voltage? Sorry? No, look carefully, right? The output is V0. The gain of the op amp is A. Non-inverting terminal is grounded. So what will be the inverting terminal? Minus V0 by A. Fine? Okay. So essentially, if A is large, this quantity is going to be really small, right? So the point I'm making is the actual swings that goes into the op amp inputs is quite small. And remember, these inputs are straightly connected to the gates of some MOSFETs. Okay. So which means the swings at the gates of some transistors is going to be really small. Whereas if I have a non-inverting amplifier, at the non-inverting terminal you have directly connected the input. Okay. So I'll have the entire swing of the input at the non-inverting terminal. What can you say about the inverting terminal? If you have an ideal virtual ground, what can you say about the inverting terminal? It will be same as a non-inverting, right? So this will also be swinging fully, isn't it? So again, as I mentioned, this is going to be connected to some gates of some transistors. So if the gate sees a large swing, what can you say about the transistor operation? Basically, it might not be in saturation, right? It can easily go to linear or cutoff if your swings are very large. And even otherwise, see, all your small signal analysis is built on the premise that the swings at all the terminals are quite small, isn't it? But here you see that the swings are quite large. So which of these two do you think will be more linear, inverting or non-inverting? Inverting, right? Because this here we see that the swings at the gates of my input transistors are really small. So my small signal linear approximation is going to be valid. Whereas here if you have a large swings, the transistor will behave more non-linearly. Your small signal linear approximation is not valid. Okay. So in general you will find that inverting amplifiers are more linear. And of course you can form these inverting amplifiers in a fully differential case also. And in general, if you have any single-ended output op amp where one of the terminals is grounded like this, you can easily convert it to a fully differential structure by replacing this ground by the copy of the same you have in the inverting terminal. Make sense? Okay. So the second thing I want to bring your attention to is the following. Let me copy this inverting amp. Put it here maybe. I'll probably also copy where is this guy? So now let us say I formed this fully differential op amp using our simple differential amplifier. Say this is carrying a current I0 and the resistors are R. So let us say I have not applied any small signal, only DC bias is applied to the inputs. So what can you say about the output? It will be same, and what will be the, let's say this Vout P and Vout M. What is Vout P and Vout M? Minus? Okay. So this is basically my output common mode. Okay. So now let us say I have the same scenario here. I am not applying any small signal inputs. So at the input I am applying only the common mode or the DC bias. So let's say the ICM for the input common mode. And at the output, my output common mode is set to something. And for our diff amp, it is VDD minus I0 R by 2. Okay. Now let me call the virtual ground voltages as Vx and Vy. So now I have formed this negative feedback around this fully differential op amp. Now what will this negative feedback enforce? If I have a very large op amp with a very large gain and I put it in negative feedback, what does it enforce? Huh? Okay, I am not talking about that. In terms of the virtual ground voltages, they will be equal, right? Vx and Vy will be equal, isn't it? Fine. That's the principle of virtual ground, right? And again, mathematically speaking, this has an infinite gain, finite output, which means the input difference must be 0. That's all. Okay. Okay. But what is the absolute values of Vx and Vy here? What is setting the absolute voltages at Vx and Vy? Something else? Yeah, we have two, right? We have both VICM and DOCM. And this basically is not taking any current. I mean, so it's as though you have VICM, two resistors and connected here like this. right? This is what we essentially have. So now can you tell me what is the voltage here, Vx and Vy? Okay, I mean first what is the contribution from VICM? R2 by R1 plus R2. Okay, superposition. Similarly VOCM by R1 plus R2. Okay, now if I choose both common mode voltages to be equal, so then what is Vx and Vy? It will be equal to the equal common mode voltage. Fine. Okay, so this is one crucial point that you will have to note, that is the virtual ground voltage, that is the absolute DC potentials of the virtual ground, is set by what here? What is setting this voltage? Input and output common mode voltage. Okay, so let me mark it here. So the virtual ground DC operating point is set by the input and output common mode voltage. The reason I am highlighting this more is this is in stark contrast to what we have in a single-ended output op amp, because if you recollect, we have a single-ended op amp like this. Okay, so this is minus and plus. I'll apply some VCM here, I'll apply some VCM here. Now what is setting this virtual ground voltage here? Yeah, it is set to VCM, but what is enforcing it? The negative feedback. The DC negative feedback around the op amp is setting this guy to VCM. So what is the current flowing here? So what should be the current flowing here? So what should be this voltage? VCM. Okay, so here what is setting my common mode voltages? Yeah, but the global negative feedback at DC. Okay, so the global DC negative feedback I have is what sets my virtual ground and my output common mode. Okay, but whereas if I have a fully differential op amp, the global DC negative feedback here, what is it enforcing? In the DC negative feedback overall we have here around the op amp, what is it saying us? What does it enforce? It just says Vx is equal to Vy. The two virtual ground voltages it makes equal, but their absolute values is actually set by the input and the output common mode. Whereas if you have a single-ended output, the global DC negative feedback is directly setting my output common mode also and the virtual ground voltage. Whereas here I will have to set my output common mode properly, and in this amplifier it's straightforward, it is set to this value VDD minus I naught R by 2. Okay, so the output common mode that is set within the op amp and the common mode I am applying at the input, together they set the virtual ground voltage. Fine? Cool. So that point is clear. Let's proceed. Let me take this guy. So this is my simplest diff amp. So what is the differential mode gain here? GM times? GM times R parallel the R naught, whatever. Okay. Now if I want to have a no, it's not by 2. See, for differential mode gain, I'll apply Vi by 2 here and minus Vi by 2 here. So this will be minus V naught by 2 and plus V naught by 2. Yeah, okay. Is that fine? The gain is just GM times R, because everything is now half circuit. Okay. So now let us say, I'll erase this guy. Now let us say I want to increase the gain. So instead of this resistor R, what can I use? Yeah, basically I have to have a current source with an infinite output resistance, and the simplest current source we know that pushes current down is PMOS. So I will have a PMOS transistor like this. and I'll connect it to some bias voltage VB. Okay, so in this circuit now, what is the differential mode gain? Gm times the R0 of this guy parallel with R0 of the PMOS, straightforward. Cool. So now here, can you tell me what will be the DC operating point voltages for the drain? No, why? I mean, if you remember, we have already discussed, right? Not the minimum maximum, not the range. If I just apply the DC bias here, right? Okay, this is biased at a current I0. No small signal. What will be the DC operating point voltage here? Can you find it? We have already looked at it, right? If we have a drain potential, how is the operating point voltage of a drain set? Either by some global negative feedback, or it should be by some VGS. Here we don't have any VGS setting it, and we just saw that the global negative feedback is not going to set my output common mode. This will work only if we have a single-ended output, right? That is why if we had a Miller op-amp, the two-stage Miller OTA, the second stage was basically this, right? And this output common mode was set by the feedback we put. But in the differential case, we cannot have that. So we need to set this output common mode within the op-amp. We cannot rely on the global negative feedback. Okay. And now if you think about it, the problem we are not able to say what this voltage is because this is biased at a current I0. So what is the current flowing in these two? Ideally, half the current. And if you look closely, this transistor is acting like a current buffer for this guy, right? I mean, if I just mark these two, erase these guys. If I just mark these two, right? This looks like a cascade, isn't it? So this is a current source. This can be thought of as a cascade above it. So together this forms an even better current source. Okay. So whatever I have marked in blue, that is essentially a current source I0 by 2. Okay. Now similarly at the PMOS side, this is also a current source, and we have biased its gate at some bias voltage VB, and let us say this carries a current IP. Okay. Now nominally I want both these currents to be equal, but of course you can't ensure it, right? So let us say IP is greater than I0 by 2. So what will happen to this output voltage V0? It will keep increasing, right? I am pushing more current into a node than I am pulling it out. So my output voltage will increase and eventually saturate to VDD. I'll have a similar scenario if IP is less than I0 by 2, then V0 will keep dropping continuously and go to ground. And let's say even magically if I set this bias voltage so that IP is equal to I0 by 2, then can you say what is this voltage? Even then I cannot say. I just know these two currents are equal. So this voltage is not going to increase or decrease. It is going to be constant. But what that voltage is, I can not say, right? So even in this case, it's going to be some undefined. I'll just write it like this. Okay. And in fact, this is a very, this you cannot have in practice because this is as though you are trying to balance a ball at the edge of a cliff. If there is some variations, this will fall either ways. Right? Similarly, you can start with this, but in practice there is going to be some variations here or there. You'll end up with either of these. So finally, if you wire the circuit up and see it, the output will either go to VDD or V0 or ground. So transistors will go to triode and cut off or whatever. So we cannot get any gain out of this. And the main problem here is because we have two current sources, and both current sources are biased independently to carry some currents, and that is why we cannot make them equal. And when you have a case like this, the output common mode is not set. We cannot say what that voltage is properly. Now, nominally, what do you want this output common mode to be at? What is a reasonable value do you think we can set it to? VDD by 2. Again, that's not a sacred number, but that's a reasonable choice. So now we want the output common mode to be set to something. Say it's VDD by 2 for convenience. And in this case, this is not set to VDD by 2 because we have two current sources which are biased independently. Okay. So what is the solution, do you think? The issue is happening because both current sources are acting independently, carrying some currents. So what could be a possible fix to it in words? Huh? Oh no. I mean, okay. Let's don't go to circuit implementation. Just first let's formulate in words. Once you know the solution in words, you can make the circuit for it. You can make hundreds of circuits for the same thing, right? See,
whatever sets the current source connected.
Sorry.
Whatever sets both the current sources, make them related to each other.
So what he's saying is, yeah. See, the point is, both current sources are now independently acting. So that is why we cannot control them. So what we should do is we can say one of them fix, and based on that you control the other. Okay. You make only one of them act independently, and you tune the other current source. And of course, this will have two ways. Now we can either fix my NMOS current and tune my PMOS current, or vice versa. Either of them will work. Fine. So let's see how we can do that. Let me quickly redraw the circuit here. Okay. So now our goal is to set the common mode at the output to be some value, say some VDD by 2, and let's say we do it by fixing the NMOS current source and by tuning the PMOS current. This is the approach that I say we are going to take. Now if I don't apply any small signals, only bias is applied here, either of the two outputs will be my output common mode. But let us say now I apply some small signals, plus VD by 2 and minus VD by 2. So this will be some common mode minus V0 by 2. This will be some common mode plus V0 by 2. How can I get the common mode from this? If I take the difference, I'll get only V0 by 2, right? I want the DC potential there. Adding is not completely correct, because if I add them, I'll get 2 times VOCM. I want only VOCM. What should I do? I'll have to average them. Let's not jump into the implementation. Let's first say it in words. Once you have something in words, right, you can find multiple ways to implement the same thing. You just need to take the average, right? So let me erase this. Okay, let's be there. So now what I'll have to do is, to get the common mode, I'll have to take the average of these two. Okay. So I'll say I'll give it to a block that detects the common mode. So it's CMD. So this is a common mode detector. That is just a fancy way of saying that I'm taking the average. That's all. Now I want the output common mode to be equal to some, say, VCM ref, which is VDD by 2 or some value you want. So what should we do now? First say it in words, right? What should we do? I have my output common mode. I want to set it to this value. So if you are going and sitting in the circuit, what will you do? Yeah, I mean some kind of negative feedback, but for negative feedback we need to send something and control something. Yeah, no, let's not don't go to the blocks that we need. In words, what do you have to do?
Find the error and then.
Yeah, we have to compare these two, right? That's all. So basically I'll have to do something, I'll have to compare the two and then control what? I'll have to control the gate voltage of the PMOS. Only that way I can control its current. Okay. Oops. Oh. So this is some block that compares the two and then I'll control the gate voltage. Okay. Now of course this block here that does this comparison is taking two inputs VOCM and VCM ref, and ideally what you want, ideally what is the relation do you want between these two? Both of them needs to be equal. So basically the difference this block takes is 0, right? So I'll say V in difference is 0 and the output is some bias voltage VB which is not 0. So what is a block that can take in a 0 input and give a non-zero output? So a block with an infinite gain, and the simplest block we know that this is an op-amp. So what I'll do is I'll put an op-amp here. Okay. Now the circuit is not complete, right? So the moment I first put an op-amp, what is the first thing you have to figure out? Signs. So what is the plus and minus here? How will I figure out? How can I find what is the correct signs?
If that voltage is more than you have to check.
Yeah, so let's assume some signs and see. So let us say this is a minus and plus, randomly I am taking. So let us say my output common mode increases for some reason. What will happen to the voltage VB? It will fall. Gate voltage falls. The current in the PMOS will increase. If the current in this branch increases, what can you say about these voltages? That will also increase. Output common mode increases. It's in positive feedback. So obviously the sign must be ulta. If the current flowing in the PMOS transistor increases, this node voltage also will increase, right? Basically you are pushing in more current into a node. Okay, this current is fixed to I0 by 2. If the current through the PMOS transistor will increase, even that node potential will also increase. Okay. So this is going to be my sign, and this technique of fixing my output common mode to some desired value using a negative feedback loop. Of course, the moment you come up with something, you have to give a name. So this is called common mode feedback for obvious reasons. Or in short, CMFB. Okay. So this essentially is a negative feedback loop that is setting your common mode. That's all. See, and one other way in which you can understand why we should have this is, if I take my fully differential op amp here, the feedback I am putting around the op amp is setting the output difference to be equal to the input difference times R2 by R1 or something. So this feedback here is only fixing my differential signal. Okay, so only the difference between the two signals is set to minus R2 by R1 times my input difference. But I have two outputs, so along with the difference between the two, I also need to set the average of the two. So we need to have a separate feedback loop for setting that average. Is that clear? See, what I am saying is, this negative feedback loop, what is it doing? It is saying that finally if I apply some input difference here, Vi, my output difference V0, that is going to be minus R2 by R1. This is, let's say, V0D and VID. So this is only the output difference. I don't know anything about the positive and negative outputs as such. To exactly know what these are, along with the difference, I also need to know the average or the common mode. So I need to have a separate negative feedback loop for setting that common mode also, and that's what we are doing here. Okay, so now let's see how we are going to implement these.
But will it be that and feedback, because it is not going into the input of the refrigerator?
That's what I mean. It's not like, see, negative feedback doesn't mean it needs to go to some place, right? I mean, for the common mode feedback, the inputs are these. I mean, you are thinking this should be the input, and that need not be the case, right? This is my differential signals, but what I am interested in is setting the output common mode. So which means these are the inputs for this loop. Okay, so let me take to the next page. Okay, cool. So now let us see how we are going to implement these. So firstly, this guy, common mode detector, is taking just the average of the two outputs. What is the simplest way in which you can take the average of two voltages? So I have two voltages, say VOP and VOM. I want to find the average VOP plus VOM by 2. What is the simplest circuit? Summing amplifier is not very simple, right? We have to have an op amp for it.
Voltage divider.
So how will you do voltage divider here?
Equal resistance.
Right, that's all. Isn't it? I just put two identical resistors, the center point will be the average of the two. So now this big block is basically now two resistors, and I'll connect them like this. Okay. So let's say I call this RCM because we are sensing the common mode, and then we'll do it. Okay, and the simplest common mode feedback loop you can have is this. See, if you actually notice here, if my output common mode increases, I want my gate voltage VB to increase or decrease? To increase or decrease? I mean, from this, what does it look like? We need to increase it, right? That's what the op amp is doing. If this voltage increases, I want my VB gate voltage of the PMOS also to increase. Okay. Now forget, I mean, instead of using an op amp, if you think about it, if this voltage increases, I want to increase this voltage. What is the simplest connection I can make here? I can connect the two, right? So that is the simplest common mode feedback you can have, wherein I'll simply go and connect the two like this, and I don't need to use op amp. Make sense? So I'll clean up the circuit and draw it in a more conventional way. So we'll have the PMOS, NMOS. So from the output I'll have the two resistors sensing the common mode, and this common mode here is directly connected to the gate. So the connection is this, that's it. Okay. So this is the simplest common mode feedback you can have. I'll just say it's CMFB. Cool. So here first let's find what will be the output common mode. So what do you think is the output common mode voltage here? See, this is the output common mode, and that is also equal to the gate voltage of the PMOS. So in ideally, I mean, finally, if everything is fine, what is the current flowing through PMOS? So what is the gate voltage? Yeah, so basically my output common mode is also equal to the gate voltage here, VDD minus VSG of the PMOS, I not by 2. Again, here the output common mode is set by this gate voltage. That's what we saw, right? drain voltage needs to be set by some gate voltage or by some negative feedback loop. Here it is a combination of the two. It is set by this negative feedback loop through the gate. That's all. Okay. Again, you can also understand this by doing the following. See, now I am interested in only the common mode signal, common mode output. So, what is the half circuit I can look at? I mean, now everything is equal, right? It's some DC bias here, say some VB. It's all common mode signals. I can draw. What is the equivalent circuit I can draw? I can draw the common mode half circuit. So if I draw the common mode half circuit, I'll have PMOS which is size 2x here. What will happen to the resistor? They both will come in parallel. So I'll have RCM by 2. Then RCM by 2. So then I'll have the NMOS, which is also size 2x, and the current source. Okay. So now it should be clear, right? The output common mode here is also the gate voltage, and that is basically this. I mean, here we have written the source to gate voltage of the transistor at a current I0 by 2. Here it is the source to gate voltage of the transistor which has 2x the size, carrying a current I0. So it's the same. Okay. So now the common mode is fine. So let's see what will, I mean, we have done something to the common mode, but our main interest is in the differential mode gain. We want the differential mode gain to be something. So let us see if it is affecting our differential mode gain. Yeah. And for that, what should I do? To find the differential mode gain, what should I do first? I'll find the differential half circuit, right? So assume that input is some VD by 2 minus VD by 2. So what is the differential mode half circuit? I have the PMOS here. Again, all the voltages along the line of symmetry incrementally ground. So gate voltage is ground. What happens to RCM? Like this. And then I'll have the NMOS like this. So now what is the differential mode gain? Yeah, I mean, forget about the minus, right? We can flip the outputs. So it is GM of the NMOS times. Yeah, so this RCM is now going to come in parallel with my original output resistance. Okay, so it could potentially reduce my DC gain. So how should I choose my RCM to be? It should be much larger than my this guy. Okay. Sorry?
How will you implement on the chip then?
Yeah, so that's the point. Now if you have a very large resistance, it will take a lot of area on chip. Now on top of it, if you have a large area, it's going to take large. If you have a large resistance, it is going to take a large area. So even the capacitance it forms with respect to ground, that will also be larger. If you have a larger something, with respect to ground, it will have a larger capacitance, right? So that capacitance will now come in parallel to the output. It will reduce your speed and stuff. Okay, so that is the trade-off. More parasitic capacitance. Okay. So this is the trade-off we have. We can't do anything. Okay. And of course, with this simplest common mode feedback, the output common mode is set to this guy, and that is actually dependent on my nu and C aux threshold voltage, everything. We can't set to the value that you want finally. Okay, it is set by process parameters. So if you want it to be set to some exact value, we'll have to have this op amp and then close the feedback loop. So we have time. Okay, let's quickly finish it today. So let's see how we'll do that quickly. So here the common mode detector again is the simplest one is the two resistors. So what I'll do, I'll put the two resistors here. Now I need to make this op amp. This op amp takes in two inputs and gives one output. What is the simplest circuit you know that can do this? Two inputs and one output, right?
OTA.
Yeah, it's a 5 transistor OTA. That's the simplest one. So I'll probably first pull this out here. So I'll draw the 5 transistor OTA quickly. So I'm going to have first let's draw the output side. This is the output, and then I'll have the inputs here. So this is my plus, this is my minus. On the positive side, I am connecting the output common mode that I am sensing. So this comes here. And on the inverting terminal, I am connecting the common mode reference, to which I mean this is the value I want my output common mode to be. Okay. So this is where I'll apply my common mode. Okay. I'll get rid of this. So this is my CMFB. So again, first let's look at the differential mode. What happens? So in differential mode, again all the voltages along this line of symmetry is going to be 0. So this guy is 0, this voltage is 0. Similarly, this is 0. So for the op amp, the inputs are 0, the output is 0. So this is not coming into picture at all. Okay. So in differential mode, we will just have the same thing. This resistor will come in parallel. Same thing as what we had here. So differential mode gain is same. Is that okay?
Yes.
So let's see what will happen to the common mode, and for that I will quickly draw the common mode half circuit. So for common mode half circuit, again these two transistors will come in parallel. So I'll erase this guy. Okay. So this is going to be 2x whatever. Now again these two resistors will come in parallel. So I can just have one of the resistors. The value is RCM by 2. So the NMOS will also do this. This is the common mode half circuit. Okay. And I'll slightly redraw this guy, I mean the PMOS, so it's more clear. Okay. So now please look at the circuit and tell me if it resembles something that you know already. Huh? What is gate booster? Oh, no, why is it gain boosting? Gain boosting we need to sense from the source and give it to gate. The same thing, right? We have to sense from the source and give it to the gate. I mean, okay, fine. This is a negative feedback loop, right? Okay, let me make it easier. I'll break the loop. Now look at the circuit. This is my 5 transistor OTA. It's a 2-stage op amp. The output here is going to the gate of a PMOS, and the output is taken from the drain. First stage is my diff amp. Second stage is a common source amplifier. So it's essentially a 2-stage op amp now, and the 2-stage op amp is now put in feedback. So I have a 2-stage op amp put in feedback. What should be alarming? What should be the thing that should be careful? 2-stage op amp, if you put in feedback, what could potentially go wrong? Stability, right? So the phase margin we need to ensure it's good. And what is the simplest way in which you can make it stable? Miller, right? So I'll have to put a capacitor. Where will I put the capacitor now? This is the second stage. Across the second stage I'll have to put. Okay, so let me probably quickly draw that. See, this is my first stage, right? And my PMOS is the second stage. And from the output, basically I have this resistor RCM and I'm putting in feedback like this. Okay, so now I have to put a capacitor CC like this, right? So the capacitor is going to come here. That's all. So I'll call it CCM. Okay. So one last thing, see, this is I am putting the capacitor in the common mode half circuit. In the final circuit, we'll have to put it properly, right? So let's me do that quickly and finish today. Yeah. See, this is the overall circuit. Here I'll have to put the capacitor properly. And in the common mode half circuit, you see that this capacitor has to come across the gate and drain of the PMOS transistor. Here I have two PMOS transistors. So where can I put the capacitor now? Gate and the drain of? I mean, is a problem clear?
Yes.
See, this is my common mode half circuit. In the common mode half circuit, I just had one PMOS, which has size 2x, and across this 2x PMOS, I am putting a capacitor CCM. Now in the original circuit, where I have 1x PMOS on either sides,
From the
yeah,
gate to
Two capacitors.
from the gate to drain, I can put two capacitors like this. Okay, each with a value CCM by 2. This is the simplest thing you can do. Okay, we can stop here and we'll continue.